Hello, 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 hello. Welcome to Work Energy and Simple Machine Lecture. This is going to be a long lecture. It's going to be, it's going to be an hour and 9 minutes. You're not going to want to listen to this lecture in one sitting. You're going to want to listen to it in several sittings. You're going to want to have some kind of paper, notebook, a pencil, take some notes, have a calculator. I'm going to be doing a few calculations. Maybe you want to prove the calculations on each page. Don't just take it for granted. So do it in more than one sitting. We're going to talk about work, force times distance, energy, kinetic and potential energy, simple machines, inclined planes, pulleys, levers, etc. Let's start right away with a problem on kinetic energy, friction, and work. A 50-kilogram box slides across the floor and its velocity decreases from 20 meters per second to 5 meters per second. What change in kinetic energy, delta KE, did the box undergo to reduce its velocity? Well, it's going to be delta KE equals 1/2 the mass times the quantity, VF squared minus VI squared. So plug in the values, prove this, make sure that I did it correctly. You'll get negative 9,375 joules. Is this reaction exothermic? Is it endothermic? Maybe you want to look up those terms before answering that question. That's part A. Now, let's do part B. Part B is going to be fairly straightforward. How much work does the frictional resistance of the floor do upon the block? Well, that's the net force is the friction. So, it's going to take a certain amount of distance to stop. Distance times the net force is going to be the work. So, if the net force is friction, it's the only force acting on the box, and it's contrary to the motion, so it's going to be negative. So it's going to be the same as the delta kinetic energy. It's going to be negative 9,375 joules. But, we don't know what the actual frictional force is unless we understand or know what the distance it took for the box to stop. What distance did it take? How far did it travel before it came to a complete stop? Well, I'm going to say in the problem that it took 20 meters. So what's the force of friction? Well, work equals force times distance. Therefore, dividing through, force equals work divided by distance. It's going to be the same value. The work is going to be the same value as the kinetic energy, which is negative 9,375 divided by 20. That's going to leave for the force negative 469 newtons. That will be the force, and that should make sense to you based on what we did with Newton's laws of motion. The force is contrary to the motion, the direction of the motion. Direction of the motion always is positive velocity. If there's an applied force, it's positive force, etc. So the negative force would be contrary to that motion, so that should make sense. Let's talk about the sweet spot. If you've ever played baseball or softball or tennis, you understand what the sweet spot is. The sweet spot of a softball bat or tennis racket is the place where the ball's impact produces minimum vibrations in the racket or bat. Strike a ball at the sweet spot and it goes faster, it goes farther. Strike a ball in another part of the bat or the racket and the vibrations can occur that sting your hand. From an energy point of view, there is energy in the vibrations of the bat or the racket. There is energy in the ball after being struck. Energy that is not in vibrations. Energy that is not in vibrations is energy available to the ball. Do you see why a ball will go faster and farther when struck at the sweet spot? It's an interesting point here. If you can hear the ball hitting the bat, if you can hear it, that means there's vibrations that are not going into the ball. There's energy not going into the ball, because sound is vibrations. So some of the energy is being converted to sound. So that's energy taken away from the ball. If you ever watch a baseball game or even play softball or baseball, you can hear. You don't hear the ball being hit when it's really hit well, really on that sweet spot. The sweet spot of the bat is approximately the center of gravity of the bat. Here's a picture of a softball player hitting the ball at approximately the sweet spot, which is about the center of gravity of the bat. Again, if you don't hear it, that means that's the less the sound, the greater the loss of vibrations, and the faster and farther the ball can go. If it doesn't sting your hands, the same thing is true. Here's a dynamic example. If I skid to a stop on a bicycle, well, the friction stopped me. What's the work due to friction? Well, it's going to be heat. I'm transferring, I'm converting that kinetic energy, the energy of motion, into heat energy. You can see the infrared camera. It's the person holding the bike is warm because of their body heat, as well as the heat of the tire. The bicycle itself is cold. Typical stopping distances for cars equipped with anti-lock brakes traveling at various speeds. The work done to stop the car is friction, force, distance of slide, miles per hour. That's a little confusing. This is out of the text. If it's anti-lock brakes, it's not going to slide, but either way. Now, you have 28 miles an hour. It's going to have a stopping distance of 10. That's going to be the slide in meters. So, is it going to be 10? We're going to say it's 10. Well, if you double the velocity, you're going to be quadrupling the distance that it's going to take to stop. If you're doubling it from 56 to 113, you're going to quadruple the distance. Instead of 40, it'll be 160. So there's energy changes here. If all the energy is being converted, there's something about the there's a connection between velocity, kinetic energy, and stopping distance. Just a kind of a dramatic example. We'll look at this a little bit more fully in the coming slides. Now, you all know what a bow and arrow is, Robin Hood, hunting, etc. Now, in the next example, I have an archer is pulling a string back, so there's potential energy there. What's potential energy? Well, it's force times distance. This is, mgh, but it's not really height because we're not going vertical. But there is a certain, there's an amount of distance involved here. How much force, the force used to pull a string back is the same amount of force the string puts upon the hand. So that force is going to be yielded and given to the arrow when you let go. And so that force times distance, when you're holding it, is potential energy, and that will become kinetic energy, and the arrow will fly. The potential energy is converted to kinetic energy, energy of motion. Now, here's an example of a pendulum. When it reaches the left picture, when it reaches its maximum height, it's all potential energy. When you let it go, some of the potential energy is being converted to kinetic energy, but it's all going to equal that same original potential energy. And then it's going to be, when it's down straight, all that kinetic energy will have been converted. All of the potential energy will have been converted to kinetic energy, and then It's going to become potential energy again. So it's going to start the cycle all over again. Well, if you go from potential energy on the left to potential energy on the right, there's no energy loss. There's no energy converted to heat. Well, heat. Heat. What is heat? Well, there's a great example of heat. Does everybody know what those are? Those are charcoal briquettes. Those are the old-fashioned charcoal briquettes. Those are when I was growing up as a kid. We would start a fire in a barbecue, and that fire would rage. It'd get very hot. It wouldn't be any flame, but the charcoal briquettes would give off this amazing amount of heat. Amazing amount of heat. And it would glow, and you could see the air shimmer above it. Gas grills today, the stones, the ceramic stones, just get hot. They don't decompose and turn to ash like the old charcoal briquettes used to. But you couldn't really cook in a flame, years ago. You had to wait until the charcoal all turned to these glowing embers. What process provides energy for rockets that lift the space shuttle into orbit? What process releases energy from the food we eat? Well, the answer is chemical reactions. There's a relationship between or among potential energy, kinetic energy, chemical energy. Potential energy could be like, let's say I have a tub of gasoline, and it's just sitting there minding its own business. You dip your finger in it, it's cool. Very, very volatile. You can smell it. It's evaporating tremendously. You have high vapor pressure. Alcohol is the same thing. It's a different consistency than water. You can see that almost in the touch of it. Its density is less than water. Well, this is potential energy. A tub of alcohol, a tub of gasoline. It's all potential energy. The energy used to send the shuttle. You have liquid oxygen, you have liquid nitrogen, you have aluminum, all kinds of stuff. First person who does do a PowerPoint presentation, or anybody wants to do a PowerPoint presentation on the energy provided for the rockets to lift the space shuttle, I'll give some extra credit. During chemical reaction, the bonds between atoms break and then reform. Breaking bonds require energy. Forming bonds release energy. Pulling atoms apart is like pulling apart two magnets stuck together. It takes energy to do that. And when atoms join, it's like two separated magnets are slammed together. Energy is released. Well, energy is not always released. If I take water apart and make oxygen and hydrogen molecules from that takes a lot of energy to do that. I'm going to take oxygen and hydrogen and slam them together, and I'll start with water and I'll end up with hydrogen and oxygen separate gases. Well, that takes a lot of energy. That's why if I take hydrogen and oxygen and I form water, it's really the reactants. The reactants are high energy content, and the products, in this case, the reactants are hydrogen and oxygen, and the product is water. You have high energy reactants, low energy products. Well, where does the energy go? Well, it went into the environment to do work on molecules on your hand. It gets it hot, and that's exothermic. It's giving off heat. Same thing if friction does to a tire. It gives off energy. It's exothermic. So if you give off energy, it's in the form of heat, and it's exothermic. Rapid energy release can produce flames. Slow energy release occurs during the digestion of food. Same thing. It's not a fire, but you certainly get energy releases. The conservation of energy rules chemical reactions. The amount of energy required to break chemical bonds is the same amount released when the bonds reform. Well, even though the bonds may be, if you reform them, they might be at lower energy levels, you've got to account for the energy. If you have water, if you have hydrogen and oxygen, high energy, going to water, low energy, the bond energy is different. Well, why is it different? Well, some of the energy went into the environment because oxygen and hydrogen are high energy, water is low energy. The amount of energy in the bonds they're not equal. Well, that's the whole point. Well, they're not equal. Well, why aren't they equal? Well, because water is more stable than hydrogen and oxygen. It's more stable. So energy was released. I don't need as much energy to hold the bonds of water together as I did oxygen and hydrogen separately. So it's exothermic. Energy is given off to the environment. Or I can use that energy to propel a spaceship or a car. Works on gasoline. I can use that heat energy, and I can make the car do work. I can make it go a distance. I can supply a force. Force times distance is energy. So ideally, the work output will equal the work input. But however, in the real world, what's larger? What's larger? The input work will be greater than the output work. So work output will be less than work input. That's why you have this reduction of efficiency. The work output a smaller number over a larger number. You'll get this strange, and again, you don't need to be a tourist or a rookie, and you don't need to say percent efficiency. You can just say, you can convert it to a decimal. So that slide should make sense to you based on all that we've done. Here's a picture of the space shuttle. Now, how do you know some of that energy from the chemical reactions that are propelling that rocket? How do you know that energy was released? What visible or what visual cues are there? What visible cues are there that is obvious that the chemical reaction is exothermic? Well, it's incredibly hot. You can see the white hot energy coming out of those rockets, those flames, those white hot flames. You are using a lot more energy than you need if that's the case, and that's what we do. We use thrust, and that thrust is inefficient either way. The potential energy of a 100 Newton boulder with respect to the ground below is 200 joules in each case, because the work done in elevating it 2 meters is the same whether the boulder is, I lift it or I use a ramp of some sort. The work done is going to be the same. So, if I take 200, if 200 joules of work is done to lift the boulder, well, what's the weight of the boulder? Well, the boulder has to be, 100 newtons. 100 newtons times 2 meters is 200 joules. So that should make sense to you. That should be intuitive sense. Now let's look at kinetic energy and the relationship between kinetic energy and mass and velocity. Kinetic energy and mass are on either side of the equation, so they're going to be direct. Velocity and kinetic energy are also on either side of the equation. They're going to be direct, but it's going to be a little bit different. It's going to be a squared function, squared direct, as opposed to linear. It's going to be parabolic. A linear relationship is a direct relationship. A parabolic equation, a parabolic relationship is also direct. So direct could be either linear or it could be parabolic. They're both direct. Well, in this particular case, 100 times 20 times 100 times 10 squared is 1,000 joules. Okay, so I go 10 meters per second, 20 kilograms, I have 1,000 joules. Now, what happens if I double the velocity? Well, it's going to equal 4,000 joules, compared to number one, which went 1,000 joules. It'll be 4,000 joules. So it'll be quadruple. It'll be increased by a factor of 4. So 1/2 20 times 20 squared is 4,000 joules. When velocity doubles, then kinetic energy increases by a factor of 4. So if you compare to number one, that would be 4,000 compared to 1,000. Again, a factor of 4. Now, in the next problem, we're going to look at a different aspect of this. Just remember, a direct relationship can be parabolic as well as linear. So this one here, I have when I double the mass, instead of 20, the velocity is the same, 10 and 10, but here the mass is 40 kilograms. When I double the mass, I double the kinetic energy because they're direct, but it's linear. It's a linear directness. So when I double the mass, I double the kinetic energy compared to number one. I have 1,000 joules as number one, 2,000 joules is number two. So, mass and kinetic energy are also direct, but it's the type of direct relationship is called linear as opposed to parabolic. Now, what happens if I double the velocity and I double the mass? Well, double the mass, it's twice. Double the velocity, it's 4 times. So that's going to increase by a factor of 8. That's pretty amazing, really, if you think about it. How I can increase the kinetic energy of an object dramatically. I go, I have an SUV instead of a sedan. I go twice the velocity. Those values are no joke. It's unbelievable. The energy increases. I'm going to double the mass, double the velocity. It's going to increase the kinetic energy by a factor of 8. Instead of 1,000 joules, it'll be 8,000 joules. So consider that before you speed, especially speed in an SUV. Here's an equation: potential energy. Gravitational potential energy is what we call it. Gravitational potential energy is mgh, where there's a height value. Remember the archer. The woman was pulling it back. It was linear. It was still potential energy. Force times distance. It wasn't gravitational potential energy. Gravitational potential energy is a vertical change of distance. Just remember, potential energy isn't always vertical, as with the archer. It could be also horizontal. So in this case, 20 kilograms times 9.8 times 20 is 3,920. So if 20 kilograms falls 20 meters on Earth, that's the change. On Earth, I have 20 kilograms times 30 meters. Okay, it's going to be 5,880. So what are you doing to the potential energy? Okay, when I increase the distance, what am I doing to the potential energy? What am I doing to the potential energy when I increase or I change one factor? Just remember, potential energy is going to be direct when you compare it to mass or height. I increase the mass, I increase the potential energy. I increase the height, I increase the potential energy. G is a constant, so we don't worry about that. We don't worry about that yet. We don't worry about that yet. But however, what happens when you do change that? You change it. You're going to go 20 meters, 20 kilograms, and I decrease. I decrease G. What are you doing? Compared to the same problem on Earth. When I went 20 kilograms times 9.8 times 20 meters, well, what was the value on Earth? So, yeah, if you compare potential energy, gravitational potential energies on Earth relative to the moon, yeah, the relationship between G and PE is also direct, linear direct, as opposed to parabolic direct. Parabolic, again, would be a square function. So on the moon, it would be, 1/6 the gravity, so the energy change would be similar. Mars is actually much smaller than Earth. You can see how much smaller it is. It's both a rock planet, but the gravity on Mars is 3.72, and the gravity on the Earth is 9.8. So the gravity differences are considerably different. Again, I change G relative to the moon. Looks like it's kind of almost tripled-ish, 2.5. I'm going to multiply the potential energy by that much. So relative to the moon, it's going to be, I increase the G, I increase the PE. Earth, I decrease G, I decrease PE. Here's a kind of a great problem. At the bottom, the ball, it's like a rocket problem. There'll be a quiz on Tuesday if you get this. If you actually read through this hint, there'll be a rocket problem such as this on the quiz on Tuesday. So you have, or it may actually be Monday. But anyway, the kinetic energy, how does it get up to that top? How does it get there? Well, it's going to need kinetic energy. The kinetic energy will decrease and potential energy will increase. At the top, the potential energy is all potential energy and no kinetic energy, as opposed to at the bottom when it was all kinetic energy and no potential energy. And then at the bottom, it's going to lose the potential energy and gain all kinetic energy, and that's just before it hits. If I have a strong man, a big guy, huh? Well, God, can you imagine lifting that over your head? Well, how much energy does he have to use? Well, that's very simple. The height is probably not quite 2 meters. He doesn't seem to be like a very tall man, but he's certainly lifting a great deal of weight. So force times distance. So it would be how far over his head. Let's say it's 2 meters, and multiply that by the mass. It looks like a considerable amount of mass. It's unbelievable. I doubt it's styrofoam. And so, how much potential energy is over his head? Well, how did it get there? Well, it needed a kinetic energy input in order to get there. So, the amount that it took to get there is equal to the amount of energy that exists when it's over his head. Now, here's a great example of the quiz next week. You have to check your syllabus again as to when that quiz will be. But the potential energy, this is a great example of gravitational potential energy. Starts off with 10,000 and goes to 0. So it's all kinetic and all potential energy now. And then as it falls, it's all kinetic energy. So the sum of the kinetic and potential energy is always, always, always the same. And you can see next door to the woman jumping out of the building, being safely caught. You can see the changes there as well. Again, this is another example, almost the exact same example I gave before, where you have the potential energy. Now, there's no loss. There's no change of any of this energy there's no change in the energy to heat. It's all potential energy changed to a little kinetic energy, and then it's all the kinetic energy, and then you convert it back to potential energy. So the height differences are the same. So remind me to show you this next week with a bowling ball and a string. It's an excellent demonstration. Whoever reminds me, I will give some extra credit to. So make sure that you remind me. And hopefully you're watching this rather long lecture. I'm going to take a little bit of a break and come back. All right, welcome back. And AMA. AMA is force output divided by force input. How do you remember that? Well, it's always going to be, for AMA or IMA, it's always going to be the larger over the smaller. So if you know that AMA is forces, hey, IMA must be distances because there's only one other larger over smaller. And that's also the case for the IMA. The IMA is going to be distance input over distance output. Now, the IMA is ideal because it doesn't lie, because distances are distances. And forces can change. In other words, the force input could be higher than it should be because of friction. But distance won't change. Distance will be the same no matter how much friction there is. Now, in the ideal machine equation, work input equals work output. In the real world, the work input will be larger than the work output. The denominator will be larger, so the efficiency will be less than 1. If they were equal, the efficiency would be 1, but in this case it's considerably larger, and so the efficiency would be less than 1. Here I have, I say B here because this really kind of refers back to another particular problem. But anyway, I have 200 joules. I take a 200 Newton rock, a 100 Newton rock, and I move it 2 meters. It's going to be 200 joules. So I take a 100 Newton rock, move it 2 meters. That's 200 joules. Or if I have a 4-meter incline, then it would be 50 newtons of force, and that would be the force input. The work output will equal the work input. It'll both be 200 joules. Now, if I use stairs instead, no work is done in moving it horizontally, neglecting friction, because we're talking about, really, with an inclined plane, we're talking about potential, gravitational potential. So lifted with 100 newtons of force up each 0.5 meter stairs, it's going to be the same. It'll be 200 joules. No work is done moving it horizontally, neglecting friction, of course. So I have the stairs broken up, and so it's going to be 100 newtons force up 0.5 meter stairs, and that will ultimately equal 200 joules. Now, let's look at some different types of machines. These are actually compound machines. I see. Do you see a lever there? Do you see a lever? It's a can opener. Do you see a wheel and axle? Maybe also an inclined plane relative to the cutter. That's going to be able to cut because it's actually an inclined plane. So we have, I see three different machines, wheel and axle. I see lever and I see inclined plane. Here I see two. I see a wheel and axle, like a almost like a jack, almost like a jack. This wheel and axle. I see an inclined plane. The cutting surface is definitely an inclined plane. This is the guts of a pencil sharpener. We're getting used to using electronic pencil sharpeners. The old style pencil sharpeners don't seem to be around as much as they used to be. But I see wheel and axle, and I see an inclined plane. Okay, so a machine can be made up of various simple machines. So a complex machine or a compound machine is made up of two or more simple machines. Here I have a lever, and it's the same as any other simple machine. I see a D on the left and a D on the right. The D on the right is DO. The D on the left is going to be DI. But I just seem to draw it here because I want to emphasize the large D on the left, small f, small d on the right, large f. Just want to kind of emphasize the whole concept of the machine. The next slide will emphasize this as well. Kind of take the machine out of it. Don't forget this is a lever. A lever, you have a fulcrum. That's kind of the triangular solid underneath the red board. That's going to be a fulcrum. So, the hard way or the easy way. The hard way is doing it yourself, lifting it straight up. The easy way is using a machine. So, this is something that, gosh, everybody always thinks that it's less work using a machine. Well, it's the same amount of work. Matter of fact, it's more than the same amount of work because of frictional forces involved. If I look at an inclined plane, this is just the same as in your equation pack. The DO is going to be smaller than the DI, and the FI is going to be smaller than the FO. The FO is the same as the weight of the object. Even though I don't have it written here, the FI is going to be the same as the applied force, or the amount of force I use to push the load up the plane. The work is the same with or without a machine. If I don't use a machine, hey, it's all the same amount of work. Again, I cannot emphasize this more. Same work, different forces, different distances, but same amount of work. And again, it's never the same amount of work because it's always inefficient, so there's always more. You do more work by using a machine than if you didn't do the machine. Here's a type 1 fulcrum, type 1 lever. A type 1 lever, the applied force, okay, is going to be the fulcrum is between the applied force and the input force. So the fulcrum is between the applied force and the output force. So even though they don't sort of draw them consistently, the man and his daughter, the applied force or the input force is going to be the man, and the daughter is being pushed up. So it's not really drawn well, but anyway, type 1 is the position of the fulcrum. Here I have a type 2. Type 2, the fulcrum is on the other side. So for this one, where the fulcrum was between, type 1, the fulcrum was between the output and input force. Here, the output force is between the fulcrum and the input force. So the fulcrum is on the other side. So you're always going to have three things. You're going to have the fulcrum, the output force, the input force. Type 1, again, the fulcrum was between the two forces. Type 2, the output force is between the input force and the fulcrum. Type 3 is a little weird, as we see this. You need, muscles in order for this to occur. So the output force, is going to be on the far right. So I'm lifting that weight. That's the output force. That's the job I want done. So the input force is going to be between the fulcrum and the output force. So with type 3, it's going to be the input force is going to be between the fulcrum and the output force. And in this one, the input force is larger than the output force. It's kind of weird because you have a muscle. That's why you have to have a muscle. It's like kind of a weird machine. Type 3 is very strange. It's different. It's contrary to all the machines we will see or have used. So know those three types of levers. So a pulley can change the direction of a force. So here it's all the same. Input and output force are the same, but the pulley will change the direction of the force. The student pulls down on the string, and the force goes, the weight goes up. So they're going in opposite directions. So a pulley can change the direction of a force. You pull down, and the force goes up, and the load goes up. So input is in one direction, input is down here, output is up. But it's the same. There's no difference in distance. It's just the machine is input and output forces are the same, as well as distances. Okay. Here I have kind of a different one. I have the output force is going to be large. See, I have two strings supporting it, so each string is going to be half the load. So the input force here is half the output force. The output force is the actual load. So the direction of the force input and output is the same, but the input force is less than the output force. So this is a little weird, little different than in other aspects. Okay, so here the directions are the same, but the pulley multiplies the forces, or divides it, multiply by the reciprocal kind of thing. Here I have two pulleys can change the direction and multiply the force. So when I say multiply the force, understand what that means. That means multiply by its reciprocal. So the input force is going to be less. Well, how much less? Well, relative to the distance, it'll be, there'll be indirect. The larger force, less distance. Greater distance, less force. So here, two pulleys can change the direction and multiply forces. Okay? So, very important. How much is it being multiplied or multiplied by the reciprocal? We'll talk. Ask me about that in class. And we're going to be doing a lab first week back on pulleys. back from the midterm. Here I have a complex pulley system. I'm lifting, or the construction worker is lifting 500 newtons, 500 units, and it's going to be considerably less. Now look at the number of strings. What is the relationship between the number of strings and the distance that it's being pulled? What is the relationship between the number of strings and the ideal mechanical advantage? Ask me about that in class. What is the relationship between ideal mechanical advantage and number of strings in a pulley system? Here I have a type 1 lever. I'm going to pull down, or the student is going to pull down 10 newtons, 1 meter, and it's going to go up 1/8 of a meter, and it's going to be 80. Okay, so it's, what is that? What does that mean? Well, it'll have a mechanical advantage and an actual mechanical advantage, ideal mechanical advantage of 10. The difference in, or 8, sorry, the difference is 80 divided by 10, or 1 divided by 1/8. So it'll have an ideal mechanical advantage or an actual mechanical advantage of 8. Now, the next one we see, we have potential energy change. The potential energy of a 100 Newton boulder with respect to the ground is 200 joules in each case, because the work done in elevating at 2 meters is the same whether the boulder is lifted with a 100 Newton force, B, pushed up a 4-meter incline with 50 newtons of force, or C, lifted with 100 newtons up each 0.5-meter stairs. No work is done in moving it horizontally, neglecting friction. This is kind of a summary of what I had before. I showed you these 3 things separately, and it's about the same thing. Okay? I'm going to take a little break, and I'll be right back. Hello. Here I have an example where some heat is produced. I have 10 joules of potential energy built up in a spring. I release that 10 joules of potential energy, and it's converted to 8 joules of kinetic energy. Well, what happened to the other 2? Well, it was converted to heat. Remember, energy is neither created nor destroyed, but can be transformed. Here it's transformed. Potential energy is transformed to kinetic energy and heat. Potential energy and kinetic energy are mechanical forms of energy. Heat is heat form of energy. So here I have a real machine where some of the heat is produced. Some heat is produced from some of the potential energy. Now, if I have a child on a sled, weight 500 newtons is pulled up a 10 meter slope that elevates her a vertical distance of 1 meter. What is the theoretical mechanical advantage? Well, I say theoretical mechanical advantage. That's out of the book. Theoretical mechanical advantage, as you can imagine, would be the ideal mechanical advantage. So TMA is the same as IMA. IMA, ideal mechanical advantage, is the same as theoretical mechanical advantage. And the ideal mechanical advantage is going to be DI over DO, or 10 meters over 1 meter. No unit labels, and the answer would be 10. The answer is 10. Now, A form of energy conversion would be, or transformation would be, this solar panel on this roof, and the sunlight, if this were passive, the sunlight would convert to heat, would absorb, the black would absorb, and you would produce heat. So the radiation from the sun is converted to heat energy. Okay, so light converted to heat is the conversion, is the transformation. Light energy to heat energy. But this is actually active solar energy, where it's going to be based on a photoelectric effect. Einstein actually won his Nobel Prize, not for relativity, which was theoretical, but for practical application. Photoelectric effect. The light hits the solar panel and you produce electricity. So light converted to electricity. Most energy consumed in America comes from fossil fuels, oil, natural gas, and coal supply, the energy for almost all our industry and technology. About 70% of electric power in the United States comes from fossil fuels, with about 21% from nuclear power. Worldwide, fossil fuels account for most energy consumption. We have grown to depend on fossil fuels because they have been plentiful and inexpensive. Until recently, our consumption was small enough that we could ignore their environmental impact. Scientists believe that global warming is man-made. Politicians are split down party lines. The vast majority of scientists believe that global warming is a result of our abuse of fossil fuels. The Middle East may have oil, but the United States has coal, enormous amounts of coal. We could be energy dependent if we change from oil to coal. The problem with that energy independency is greenhouse gases are produced, carbon dioxide. Methane can also be a greenhouse gas, 24 times worse than carbon dioxide. Methane comes from natural gas that's down in the earth that could escape and cause havoc. With the mining of, with the big Gulf disaster, the Gulf oil disaster, a year and a half ago or so. Well, that produced a lot of natural gas as well as oil came up. So did a lot of natural gas, and that can pollute the environment. Natural gas, CH4, natural gas is methane, CH4, that can have 24 times the effect. But let's get back to this. But things have changed. Fossil fuels are being consumed at a rate that threatens to deplete the world supply. Locally and globally, our fossil fuel consumption is measurably polluting the air we breathe and the water we drink. Yet despite these problems, many people consider fossil fuels to be as inexhaustible as the sun's glow and as acceptable as mom's apple pie, because these fuels lasted and nurtured us through the 1900s or the 20th century. But that's not really the case anymore. It's we've got to start thinking about other forms of energy, and in order to produce electricity, we need, a lot of things. I'll talk in class about the national grid, and what does that have to do with anything? But financially, fossil fuels are still a bargain, but this is destined to change. Environmentally, the costs are already dramatic. Some other fuels must take the place of fossil fuels if we are to maintain the industry and technology to which we are accustomed. The French have chosen nuclear, with about 74% of their electricity coming from nuclear power plants. What energy source would you choose as an alternative power? I'm a little bit skeptical about nuclear because, it's cheap. I could hold in the palm of my hand 11 cents of uranium, and that would be hundreds of 100 train cars full of coal as an equivalent. But yeah, it's cheap, but it's also deadly. It's what do you do with the waste products? And then what makes nuclear expensive is the safety precautions that have to be taken. But after all that's said and done, what do you do with the nuclear waste? Where do you put it? It'll be around for hundreds of thousands of years. So I'm not sure nuclear is a good alternative. This is really up to you to decide, up for you to decide, up to you to decide. Because the adults, the people who are in their 50s and 60s, are not going to be around for the debate much longer. So students are going to have to pick up the slack for this debate, and things have to be voted on as well. In the meantime, we shouldn't waste energy. As individuals, we should limit the consumption of useful energy by such measures as turning off unused electrical appliances, using less hot water, going easy on heating and air conditioning, and driving energy efficient automobiles. By doing these things, we are conserving useful energy. There are really 4 things that you can do when you're a homeowner, or you can encourage your parents to do it. But again, it's expensive. You can make sure your house is white. Make sure your roof is white. Make sure you have new windows, good windows. Make sure that your furnace is relatively new and efficient. So, and you're also your air conditioning. So make sure your heating and air conditioning units are efficient. The white roof will conserve tremendous amounts of energy. Insulate your attic. Make your house white. It's amazing. What cools faster? If I have coffee with cream or coffee black, and they're both the same temperature, at the same temperature, what's going to cool off faster? White coffee or black coffee? Is there a difference? Very interesting. Interesting to consider. Now, one of the problems with natural gas and oil is that it comes from the ocean, the Gulf of Mexico, various places around the world, and that can cause tremendous problems ecologically. In how many reasonable ways can we reduce energy consumption? Well, we talked about just making sure your own homes are insulated and white, and the appliances are energy efficient. That's a tremendous way of saving energy worldwide. Not only do we want to look at solar power, but we also want to reduce the energy consumption to begin with. When electric current passes through water, bubbles of hydrogen form at one wire, and bubbles of oxygen form at the other, at the different poles. In a fuel cell, the reverse process occurs. Hydrogen and oxygen combine to produce water and electricity. Fuel cells are enormously efficient. Fuel cells are enormously efficient. The combustion engine that runs on fuel, fossil fuels, are enormously inefficient. They are not in the slightest bit efficient. Electricity can be light. Incandescent lamps can be extremely inefficient. So the efficiency of the energies we use can make a big difference in how we determine as a society, how do we conserve and how do we produce energy? How do we convert from one form of energy to another? How do we transform energy to make it useful for our daily lives? Okay, here's a lever. That's one simple machine. I'm going to show you 4 basic simple machines to review. This is coming near the end of the lecture. It's been quite a while since the lecture began. So hopefully this has been useful for you. But anyway, the first is a lever. This is actually a type 1 lever. What's a type 2 and a type 3 lever? We have a wheel and axle. Now, I want you to do something for me. I want you to write down lever type 1, 2, and 3, and then look at an application for each. That would be very important. Wheel and axle. Wheel and axle. What is a wheel and axle? Well, car, a pulley. You have block and tackle. Pulleys block and tackle. The block is actually a wheel and axle. The tackle is the string that you put through the pulley. But a pulley is actually made of block and tackle, a wheel and axle and the string. So a pulley can be actually a use of a wheel and axle. So here's a pulley. The white string going up or down, or whatever the case may be, is going to be a wheel and axle. The string is the tackle. The block is the green is the block. That's going to be a wheel and axle. So this is the third machine we're going to look at. We're looking at levers. We're looking at wheel and axle. We're looking at pulleys. We have pulley systems where you have more than one wheel and axle. You can have more than one string. We'll use 4, 3, 2, and 1 wheels and axles in our pulley when we do the lab next week. Here's the inclined plane. Now this is going to be the major. This is the major simple machine that we use is going to be a inclined plane. That's the one where the hippo coming out, slipping into the Lake Malawi when we looked at Newton's laws. Well, Newton's laws, we looked at a lot of simple machines. We looked at a lot of problems using an axle. I'm sorry, not an axle, an inclined plane. So inclined plane was used for a lot of problems we did in Newton's laws. And I would say, the easiest way to teach simple machines is the use of the inclined plane. It's the most direct, so it's no wonder that a lot of the problems in the book and a lot of the problems we've used and done have revolved around the inclined plane. Here's an inclined plane where the work input is going to equal the work output. We're not talking about any kind of friction here. The woman is pushing ice up the ramp. You can see her smiling, not straining at all. You can see the fellow there, the man, trying to lift up the ice 1 meter as opposed to sliding at 5 meters. The ideal mechanical advantage would be the DI 5 meters over the DO 1 meter, which would be an ideal mechanical advantage of 5. So essentially it would be, what would if you have the weight, would be the FO. It would be the weight, the guy's holding the weight. Well, the woman would be 1/5 the weight if it's going to be a mechanical advantage of 5. So whatever the weight is, it's 1/5. Here's a wheel and axle. You're talking about a car jack. Car jack is going to have a very large mechanical advantage Here I have it's kind of a wheel and axle. The screw part, the big blue screw part, is going to be the axle. The wheel is going to be the 16 centimeter, the 16 centimeter with a 16 centimeter radius. The handle is actually the radius of the wheel. So the mechanical advantage, the ideal mechanical advantage would be 0.16 meters divided by 0.002 meters. 2 millimeters is 0.002. 0.16 meters is 16 centimeters. So 0.16 meters divided by 0.002 meters would be 80. So, you have a pitch, which is the 2 centimeters. So you have a wheel and axle. Also an inclined plane there. There's an inclined plane. If you see that, you see the inclined plane. Any kind of screw, a screw that you screw in the grass, screw in a piece of wood, whatever, that's all inclined plane. So I see a wheel and axle, and I also see an inclined plane. And again, for a jack to work, it has to have a very large ideal mechanical advantage, and it has to be pretty efficient, because you don't want to be, spending a lot of the energy that you're going to be using to work this machine. A lot of that being converted to heat and wasteful energy. Whatever energy you pump into this, you want it to be, you want to convert it directly to mechanical energy. Okay, so that's it. That's your lecture. All the best on your test coming up in a couple of weeks. And have a great day, and goodbye.